Hi again. So this session we're going to talk about another challenge in working out mitigation policy, and that's really the issue of discount rates, or really the issue of how do we compare the benefits, which are largely in the future, of reduced climate change to the costs of mitigation, which are largely incurred in the current period. So reducing greenhouse gas emissions means that you and I change our decisions today, and most of the benefits are less pollution, a smaller global stock of greenhouse gases, less climate change, less costs of adaptation for future generations. So how do we compare these benefits in the future with current costs? So economists use what we call a discount rate for this purpose. So if we want to compare a dollar in the future with a dollar today, we discount or divide the future dollar by 1 plus what we call D, the discount rate. So for example, if the discount rate is say 1%, then we would divide future dollars by 1 plus 0.01. If the discount rate was say 20%, then we would divide future dollars by 1.2. And of course we'll have to argue a little bit later on, why would we want to do that? And the trouble is that there are different ethical, economic and political arguments about the choice of the value of the discount rate. So yes, there's uncertainty about the magnitude of climate change, there's uncertainty about the costs and benefits of climate change, and just to make it a little bit more complicated, there's uncertainty about the discount rate. So this subject, of course, is always one about debates. Now, why is it important? Well, the larger the discount rate, that is essentially the less we care about the future relative to the present, the smaller would be the chosen level of mitigation, and the greater would be climate change and expenditure on adaptation in the future. So let's again just think about the costs and benefits of policies to reduce pollution. Costs of mitigation to reduce greenhouse gas emissions involve changes in decisions about less polluting but more expensive and less beneficial options. So we have to change our production methods, like choosing solar rather than coal-fired electricity, about using more energy efficient production methods and washing machines and home appliances. We have to change our decisions about which products are produced and consumed. So we have to make decisions about walking and bicycling to work or university rather than by driving a car. So these costs are front-end loaded and essentially fall on the current generation. The benefits of less climate change, less of mitigation, smaller stock of greenhouse gas emissions in the future, and less climate change. Less expenditure then on adaptation to changes in climate. Most of these benefits go to future generations. So just to highlight again, our challenge is how do we compare the costs of mitigation, the front-end loaded stuff, with the benefits of less pollution down the track for future generations. So the effects of discounting is, again, we're trying to get future dollars in terms of today's values. And what we use is the discount rate to do that. Now we can simplify the story in choosing a discount rate. We talk about constant prices or real prices. Essentially what we're doing is we're ignoring the effects of inflation. Now most of the developed countries inflation is only in the sort of 2 to 5% range per year. But in some developing countries, we've had inflation in the tens, if not hundreds of percents. So we try and ignore different prices. We think all in terms of, say, 2014-15 prices. So suppose we want to compare $1 in the next 20 years, that's the future generation, with the current value of $1 for this generation. So we're going to set up a simple table here with the value of D, the discount rate, and I'm going to set that up as the discount rate per year. And I want to find the present value of future dollars. Okay, well now we know that if the discount rate's equal to 0, $1 is equal to $1. Now we want to go to the case where the discount rate is equal to 1%. And what I want to show for you is that $1 in the future with a discount rate of 1% in 20 years' time is only worth 82 cents. So here's the way I get to that result. So I have $1 in the future, and I want to divide it by 1 plus the discount rate. That's using my formula up here. Now what am I doing in this formula? Well, I've still got the $1 up on the top of the line. I've got the 1 plus now that discount rate is in an annual basis. I'm talking about a 20-year period. So I'm going to add 0.01 for the annual discount rate, and because that is multiplied over each of the 20 years, I'm going to raise this to the power 20. And so that's how $1 in 20 years' time, if I use a discount rate of 1%, is only worth 82 cents. If I push the discount rate up to 3%, then the present value of $1 20 years hence is only 55 cents. And if I was to go all the way to 6%, $1 in 20 years' time is only valued at 31 cents. So that becomes really important in this debate about how do I compare the benefits, the future benefits of less climate change against the current costs of policies to reduce pollution. So the higher the value of D, the less we value future generations. So how do we decide the value of the discount rate? I'm going to look at two models for you. Simplest model is think of you and I as the current generation. If we save today, essentially what we're doing is postponing consumption until the future. So for example, if you're paid $10 a week by your government or by your parents to go to university, I could spend it on entertainment today, that's current consumption, or I could put it in the bank and save it for a holiday after classes and exams finish. And if I was to put it in the bank, I would hope I would get some interest and it would generate some more future income. So if I put that $1 in today, it would be the current dollar plus it would be augmented by the interest rate R. So for example, if I was to get 5% interest, $1 I put in the bank today would be worth $1.05 at the end of the year. So that's one way of thinking about the discount rate. And why do we get that return? Well, it's a trade-off or benefit to us for postponing a good night out today for a better holiday at the end of the year. And of course the bank uses that money for somebody to build machines or run a business and make more production down the track. So then we would set the discount rate equal to that interest rate. Now in most countries that real interest rate R is around 5%. Remember, that's clearing the story for inflation. So that's one model that we would use to choose a discount rate. Another model is we regard each generation as of equal value to the current generation. And that is ethically and philosophically a very strong position to take. Now, if you literally took that, $1 for the future generation, because they're of equal value as the current generation, is worth $1 today. That would imply that the discount rate is equal to 0. But there is a small risk that we'll have a global disaster. An asteroid will hit us, or we'll start off a nuclear war, and future generation won't exist at all. So many people would say, well, I would discount future dollars by that very, very small probability, but something greater than 0, that the world won't exist for our future generations. A more tenable argument is that future generations will have higher incomes. And almost all projections for every country is that we will get smarter, new technology, better work and management practices will actually have higher incomes per capita. And in general, we value an increase in income of, say, if I had $1,000 a year, an extra dollar of income is worth quite a lot. But if I had an income of $5,000 a year, an extra dollar is not worth quite so much. So in that sense, we would value future dollars a little bit less than current dollars. And that would suggest then that the discount rate D should be somewhat greater than 0. Now, this is essentially the model that's been used in the Stern Review for the UK in 2006, and by Garneau for Australia, and by many other people who analyse climate change. So they suggest numbers of the order of discount rate of 1 to 2% per annum, a number that's substantially less than the current generation model. So if we can conclude, the choice of the discount rate is important to choose what we call Q star, the optimal level of pollution reduction. And if you recall earlier sessions, that's where the marginal abatement cost is equal to the marginal external cost. But also, discount rates are important for lots of other investments. So we can make life better for our future generations by investments in our education, in road and rail infrastructure, in looking after the environment, as well as in preventing climate change. So we tend to use different discount rates for different ways of looking after future generations. The question is that a smart way to go? Economic efficiency would say you would want to use a similar discount rate for all types of investments in future generations. That would tend to want you to want to use the current generation model. Discount rate maybe of the order of 5%. On the other hand, many of us feel that future generations should be treated the same as current generations. And this would lead you to a discount rate much lower, something like the 1 to 2% used by the Stern Review. So these are just an idea of some of the debates that are very important in deciding on climate change policy.